Hello everyone. Today I'm going to present a paper, Low-Rank Adaptation of Large Language Model Rescoring for Parameter-Efficient Speech Recognition. This is the work I've done during my summer internship at Amazon Speech, and this paper has been accepted by the 2023 ASRU conference. In this paper, we introduced a new framework called LORB, which is a shortened version of Low-Rank Adaptation for Rescoring BERT. And we further introduced a multi-loss training strategy to help alleviate the overfitting during the parameter-efficient fine-tuning phase. So this is the agenda of today's presentation, where I will start with the background technology used, and I will introduce our method, including the proposed framework, as well as the multi-loss training strategy. And finally, I will summarize our work briefly and introduce a future direction of the work. In the most state-of-the-art speech recognition system, there are two phases. In the first stage, there is the acoustic model, which includes an encoder and a decoder. So the encoder will transform the raw acoustic sequence into the acoustic features, and the decoder will further transform that acoustic features into the n-best hypothesis. And then in the second stage, there will be a language model that is used to transform that n-best list hypothesis into a list of the ranking scores, and the final language model will pick up the hypothesis with the highest score as the final prediction here. There is a recent model called Rescoring, which is also introduced by Amazon in 2022. So there are two components in the Rescoring model. The first part is the BERT, which is famous for its bidirectional attention to capture the context of the input sequence. And the BERT model will convert the input sequence into the hidden representation for each of the token. And there is another feedforward network in the Rescoring BERT, which is designed to learn the rescoring to specific parameters. So here, the feedforward network will be trained with the minimum word error rate objective, and will be used to get the numerical value for the input sequence. And so regarding the motivation of our work, we consider two practical problems here. First of all, there is very high training budget for scaling up the Rescoring model, considering the GPU memory requirement as well as the limitation of the training speed here. And for another, we observed that if we fine-tune the Rescoring model on different business domains in the production setting, we observe the performance. There is a performance degradation on every business domain. And there is actually previous work that proving that adding additional regularization laws during the adapter fine-tuning of the large language model could help to alleviate such performance degradation. So to tackle these two specific problems, we introduced the framework LORB, which is a shortened version of low-rank adaptation for the Rescoring BERT. We reduce training time to up to 6 times compared to the traditional full fine-tuning, and can reduce up to 32% of the GPU memory. So to tackle the second problem of the generalization degradation, we introduced multi-loss training strategy, which is also the first time study in the low-rank adaptation research in the speech recognition field. Specifically, we introduced a correlation-based loss in addition to the word error rate loss. Let's recall the LoRa technology here. So for the pre-trained weights in the large language model, we could apply the low-rank decomposition to the change of the weights, denoting as delta W equals to the multiplication of the WB and the WA, while the WB is initialized to 0, and the WA is initialized to Gaussian distribution. So how do we apply low-rank adaptation to the Rescoring BERT? We applied two different strategies to the two components inside the Rescoring BERT model. First, for the BERT model, we freeze pre-trained weights of the BERT, and we insert the trainable low-rank matrices into the BERT modules. These matrices have the low rank compared to the initial dimension of the bird weights, so that we can save a lot of training parameters here. And these trainable matrices are inserted into specific modules such as the query and the value inside the multi-head attention, as well as the feed-forward weights inside the transformer blocks. And to be noted here, for the feed-forward network, we do not freeze any pre-trained weights. Instead, we continuously fine-tune the feed-forward network using the same training objective, the minimum or error rate training objective, similarly as the Rescoring. As for the multi-loss training strategy, we propose the correlation-based loss, and we'll present how it works here. So this is the Rescoring bird, and it takes the input of the sequence, which has the classification token as the prefix here. And the Rescoring bird here will computes a prediction numerical score for this input sequence. And we will compare that prediction score, prediction transcription against the ground truth transcription, and we compute the error rate loss here. So for the correlation-based loss, we simply take this hidden representation of the classification token, and let's suppose that there are only 5 dimensions in this hidden representation. What we do is we compute such a correlation matrix where each cell in the matrix represents the Pearson correlation between the dimension I and the dimension j. And we further take the distance between this correlation matrix with the identity matrix and use this distance score as the correlation-based loss. And this will be added to the error rate loss as a final loss. So how does this correlation-based loss help here? Intuition is like, if we minimize this distance between the correlation matrix and identity matrix, the dimensions inside the correlation matrix will be less likely to shrink to 0. And the representation, the hidden representation distribution will look like the right figure here, which is spread more evenly and isotropically inside the hidden space, so that it has a stronger generalization capability than this left figure. For experiments, we compare our methods with regard to the full fine-tuning as well as other parameter-efficient transfer learning methods such as the adapter, bifid, and prefix tuning. We first evaluate our methods on the internal datasets, where we specify as target and non-target datasets. Target domain is the messaging data which we use to fine-tune the Rescoring bird, and the non-target datasets are the domains like general shopping and knowledge, which are the datasets we use to evaluate the generalization capability of the fine-tuned Rescoring bird. And all the numerical values here in this table are the relative or error rate improvement on the test sets. If we look at the target column here, we observe that the LORB as well as the LORB with the multi-loss training can achieve a comparable performance with regard to full fine-tuning here. And if we look at the non-target columns here, we can see that LORB itself has achieved a remarkable improvement on all the out-of-domain data. And specifically, the correlation loss could help specifically on the shopping domain. So we further evaluate on the public dataset LibreSpeech and public model checkpoint bird-based case using the same whatever rate training objective. So similarly here, the LORB as well as the multi-loss training could help to achieve comparable or even better error rate on the test claim and test other set. So to briefly summarize our work, we first introduced a brand new framework, LORB, which is an efficient and scalable framework for domain adaptation of the Rescoring bird model. And we further introduced the multi-loss training to alleviate the overfitting and enhance the generalization capability of the low-rank adaptation Rescoring bird model. Thank you for your attention, and if you have any questions, feel free to contact me and other corresponding authors here.